This video is going to be about electrophilic addition. What is electrophilic addition, the general reaction mechanism for it, and then a specific example. So let's start with what actually is electrophilic addition. Well, when we break the word down, philic means to like. Addition obviously means adding something in. Electro stands for electrons or sort of a negative charge. So what we gather from this is it's something that lights electrons or negative charge and it adds in. So when we look at a alkene, a simple alkene, we remember the actual bonding is a carbon-carbon double bond. So one bond is a sigma bond where you've got these hybrid orbitals, which in this case are sp2. If you don't know what a hybrid orbital is, refer back to one of my videos about it. So you've got a shared pair of electrons in there. But then to form the double bond, you've also got this bonded pi system. Now, the electron density of this is something like that, and you have two electrons there. If you can't remember the shape of a p orbital, again, look back at my other videos, but you've got two p orbitals that look like that, with the carbon being here, carbon being here. These then overlap to form molecular orbitals, these kind of shapes. And then you've got your hydrogens being bonded off there. Now what this means is you have a high electron density around this carbon-carbon double bond, and this is really good because you can actually break this pi system and add addition things into it, atoms into it. So look at the general reaction mechanism of electrophilic addition. So you've got this alkene. These could be R groups, they don't have to be hydrogen. I just put hydrogen so it's the simplest example, ethene. And you're reacting with two atoms that are joined together. I just put them as A and B. It can stand for any atom. And the double bond breaks and A and B are added into the molecule and it forms an alkane as the double bond is broken. So if we look at the general mechanism using A and B, one thing you have to notice, if there are no dipoles, for example in H2 as they're two equal atoms, then a catalyst may be required. So I know these mechanisms are very similar to carbon-carbon triple bonds. If you want to add in hydrogen, you have to use something called Lindlar's catalyst. Okay, so if we look at this mechanism, if we treat A as being delta positive and B as being delta negative, then these are the common examples that you'll come across. So this has a slight positive charge, this has a slight negative charge. Now we have a huge area of electron density around this carbon-carbon double bond compared to a carbon-carbon single bond. This means this slight positive charge is actually attracted to that. And if you remember from a brief summary of dipoles in one of my other videos, the two electrons are closer to the delta negative than the delta positive atom. This means as we approach this high electron density area, A is not only attracted, but it almost pushes those electrons further away because they're negative as well, breaking that bond. So what actually happens is this carbon-carbon double bond breaks, a pair of electrons moves to this delta positive atom, and the pair of electrons from this bond of AB breaks and goes to B. If you don't know what these Kelly arrows are and the delta symbols, then go back to the basic mechanism video I made earlier and it explains all that. So this then forms an intermediate. If you remember from the basic video again that reaction pathways, you haven't just got reactants going to products, you have these intermediates before you get to the product. So the first intermediate in this is carbon-carbon single bond, as that double bond just broke. You've still got your hydrogens, they haven't gone anywhere. But now you've added A in. Now in this case, because it's a symmetrical molecule, A is going to go onto this side, or it could go to the other side because it's symmetrical. And then you leave a positive charge, you have sort of a carbocation, because it's lost an electron because it was sharing electrons there and now it's not sharing them anymore. So you have a positive charge. And B minus is also left with a lone pair because that bond is broken and gone to B, to give it a minus charge because it has one extra electron, that carbon has one less electron, so it's positively charged. Now what happens is, just like magnets or anything, negative charge is attracted to positive charge. Like I said, in magnets, like north is attracted to south, the opposites. So what actually happens is this lone pair, both electrons go and form a new bond with this carbon. So a double-headed arrow is used, which then forms the product that we want. So we've still got the same hydrogens. We've still got A that was added in earlier, and now B's also been added in. So electrophilic addition. If we take a real-life example with HBr, what we get is bromine is a lot more electronegative than hydrogen because the charge density in the nucleus and things like that. So what happens is this double bond breaks as the hydrogen is delta positive, and this double bond breaks, so the electrons go to the delta negative atom, which forms the intermediate of carbon-carbon single bond. Still got the H's remaining from the start, but hydrogens come in this time. So you have a hydrogen on there, and you have the carbocation on this carbon. Again, it could be the other way around. The hydrogen could add to this one, and the carbocation could be there because it's a symmetrical molecule. Now you've got bromine with a negative charge, and that lone pair will then be attracted towards the carbocation, the positive charge, and react to form our final product, which is bromoethane. So that's all for this video. Please like, share and subscribe for more videos. If there's any topics you would like me to cover that I haven't already, just let me know in the comments below or send me a message, and I hope I can help. Thank you.